Hi, and welcome to this video on artificial intelligence and machine learning, where I explain the basic ideas of how it works. My name is Kasper Green Larsen, and I'm a professor at the Department of Computer Science at Aarhus University. So let's start out with just what is the plan of this video. So first of all, I'm going to go through the basic ideas and the math that underlie machine learning and artificial intelligence. This is going to, I guess, be the most technical part, but will be necessary to later understand the inner workings of neural networks and how they can be used to solve tasks such as image recognition, figuring out what is on an image. Then we'll move on to explain the basic ideas of so-called large language models and chatbots like ChatGPT. And we'll have a look at also tools for generating images based on a text prompt, generate an image of a cat or what have we. And finally, we're going to conclude with some of the technical and ethical challenges that relate to AI. Okay, so first of all, we'll dive into the technical details of how does it actually work. What is the math that makes this AI and machine learning work? So let me start with a simple example first, and let's build up from there. So on the left-hand side, you see my head of department. He's out on his bike, and if you keep a close eye on his watch, you'll notice that in a few seconds, um, it's asking him, "Are you working out? Are you on your bike?" Right? So somehow the watch detected that he was on his bike and suggests that he's doing a workout. So of course, this smartwatch is equipped with sensors that collects data, in particular heart rate and speed. And then there's some machine learning model or AI that has been trained to find patterns in this data. And using this as a working example, we'll start to kind of introduce the first ideas of AI. Okay, so how could one train such a smartwatch, right? How can we construct a smartwatch that can detect that we're on a bike? So let's make it simple for now and just say, okay, we just have to distinguish, are we driving a car or are we on a bike? So just the two cases. So this basically starts out with gathering some data. Okay, so you have a bunch of people or users that you send out. Some of them you send out on the bikes, some of them you send out in their cars. You measure, for instance, their heart rate and the speed. So maybe my head of department has a heart rate of 150 and he's going 16 miles per hour. Someone has a heart rate of 70, is going 56 miles per hour, and so on. And for each of these users that we send out, we know whether they were on a bike or they were in their car, right? So this is what this small symbol below them indicate, right? Was this someone on a bike or was it someone in their car? So we gather all this training data, and then we're gonna, we could also translate to kilometers per hour if you're more comfortable with that, but I'm gonna stick to miles per hour for the rest of this video. Okay, so basically, if you take a look at this data, now I guess I simplified a little bit compared to reality, but it'll probably look something like this, right? So it's probably all the people that have a high heart rate but a slow speed are most likely on their bikes, and a slow heart rate and a high speed are most likely in their cars. But it's not completely true, right? Someone driving down a mountain on the bike might be going really fast, or maybe a nervous driver would have a high heart rate. But it'll probably, in a simplified setup, look something like this. Okay. So what you could do is you can kind of see, at least in this setup here, there's kind of like this nice line that separates all the bikes from all the cars. And so the idea is to find this line that separates the bikes from the cars, and then we're going to use this line to make predictions when you're wearing your watch of what activity you're doing. But maybe first of all, how does the computer find a line that kind of separates the bikes from all the cars? This is basically done by using some basic math that you've seen before. If you remember the equation of a line can be described by this equation y equals ax plus b, where a is the slope of the line and b is the intersection with the y-axis, the offset. So basically what happens is that a so-called algorithm is going to try a lot of different values of a and b. So it could look something like this. You try a slope of 2 and an offset of 3. Now you have a line, and since you have all this training data available, right, you already sent people out on their bikes and their cars, you can check how good is this line if I want to say I want to have all the cars on one side and all the bikes on the other side. And this line is not particularly good at doing that. So you look at a bunch of different lines until you find one that's good at splitting your data into two pieces. So the green one here in the middle, it does the best job. It perfectly splits or separates all the cars from all the bikes. So now we've found a line, and now we're going to use this line to make new predictions. So now let's say you're wearing your watch. Your watch is measuring that your heart rate is 85 and your speed is 70 miles per hour. So you have a new data point, and we have to, this time, we don't know what activity you're doing. This is what the watch wants to predict and wants to give a suggestion. So what you can do is you already have found this line based on your training data. And so what you're going to do is you're going to compare yourself to this line, right? So you're going to go out on the x-axis to your heart rate of 85. You're going to go on the y-axis to a speed of 70 miles per hour. And here you can see that you are above this line that you computed from the so-called training data, which means you're on the same side of the line as all the cars. So we're going to predict that you are currently in your car. Then the general hope that underlies this machine learning and AI is that if the line that you found performs well on the training data, meaning it's a good split between the cars and the bikes, then hopefully it's also going to be good on new data. That's the basic idea. Right. So, but maybe just a word of warning here. Just finding such a line only works if the data that you've gathered is actually separable by a line. So maybe let's see what I mean. Like so here with the heart rate and speed, at least in my simplified setup, a line nicely captures whether you're on a bike or in your car. But maybe you measured something else. Like let's say maybe the data that you have available is the day of the month that the wearer of the watch has his or her birthday, and then it could also be the altitude. Say how high are you above sea level? Now, if you gather a lot of data, you have people in the bikes, people on the cars. You and the data you gather is the altitude and the birth date. Then probably the data will look something like this instead, right? There's no real pattern here. There's definitely not a line that nicely separates the cars from the bikes. So here you cannot really use a line. So really what you do is that when you're doing this machine learning and AI, you use a model that you assume gives a useful or is representative of reality, right? So there is actually the kind of like, there should be a line that splits the data nicely if you want to use a line. Okay. Let's have one more simple example before we move on to the more interesting types of machine learning. So let's say that you've gathered historic data of house sales. You know the price of the house when it was sold, you know the number of square feet of the house, you know the construction year, and so on. A natural task you could try is also to predict the sales price. Like what price can I sell my house for? And how could this be done? So here we're going to do a super simple setup again, where let's say the only data we have available on the house is the number of square feet. Of course, normally you have more data available, but let's take a very simple example to make the points as clear as possible. Good. So again, you have historic data, right? So you have all this data that you gathered, all the houses that have already been sold. So for all the data that you know what the sales price was, and you know what the number of square feet was, and you can draw them again in this plot here that you see. And now you have a new house that you want to sell. You know the number of square feet, but you don't know what is the realistic sales price. And here you want to use the historic data to make a prediction for the sales price. Okay, so how can this be done? So here again, at least in this simple setup, it looks again like there's this nice linear behavior. You can kind of draw a line that pretty accurately captures the relationship between the number of square feet and the sales price. Indeed, if every house had the same price per square feet, it would be a perfect line, but they don't. But it's kind of like the bigger the house is, the higher the sales price, and maybe a line is a reasonably good explanation of the sales price. But indeed, if you insist on this being, you find a line like this one, the way you could make a prediction for the price of this house that you want to sell is, well, we know the number of square feet. So we could go out on the x-axis to the number of square feet was 2,200. You go up till you hit the line. And then you see where's the line at on the y-axis. It's at, say, 620,000. So then you can predict that the sales price for this house is 620,000. Good. So again, you can ask yourself, right, what I drew this line here and it looks kind of nice, but it's not a perfect line through the data. How does the computer find this best line? And maybe more importantly, which line is even the best line? Right? In this case here, there are many different lines you could use. So at least the orange one seems pretty ridiculous. But how do we even decide that the green one here is the right line to use? And this here we're going to introduce another very important and central concept in machine learning and AI. So this concept is known as loss functions. So the basic idea is that we want to give a penalty if you make a mistake when you're predicting. So let's say the actual sales price of this house is 670,000. This predicted sales price that you predicted is 620,000, which means now we want to give a fine or a penalty for making an incorrect prediction, right? Because we're off. Our predicted sales price is not the right one. We predicted 620,000. The actual price was 670,000. So we want to give a fine or a penalty for making a mistake. And the penalty we want to give should be proportional to the mistake. So we want to penalize for making a mistake of 50,000 in your prediction. And the general idea is that we want the fine or the penalty to be more expensive the more wrong you are, right? So huge mistakes in predictions should cost more. And then again, we hope that if we can now find a line that if we use it on the training data to predict the prices of all the houses in our training data set, if it has a small penalty on this data, it's also going to have small penalty on new data. So let's get back to this idea over the next couple of minutes. Basically, the basic analogy maybe to keep in mind is that if we punish people for mistakes or crimes, then they hopefully try to avoid them in the future. That's at least some idea of these penalties. Okay, so how large a penalty should we give? Right, so let's say that out here on the x-axis, we say this is the predicted sales price. So let's say we predict 620,000 and the actual sales price was 670,000. What should we penalize by? So out here on the y-axis, we're going to draw how big a penalty should you give depending on what you predicted. And a very standard choice here is to say you're going to pay the mistake squared. So what does that mean? It means it takes the actual sales price, subtract off your predicted sales price, and square that number. And just so you remember, right, x squared, if I square a number, I just multiply it with itself. So this is going to look something like this. If you predict the exact sales price, then the penalty is going to be 0. And the further away you go from the actual sales price, the penalty that you pay gets higher and higher. In our example here, if you predict 620,000, your mistake is 50. And so you pay 50 squared, which is 2,500. That's the penalty that we're paying. Okay, so we want to give, in this case, a penalty of 2,500 for making a mistake of 50 in our prediction. We can also see here, if I had instead predicted a sales price of 900,000, and the actual price was 670,000, then the penalty that we would get would be much, much higher. It would be the difference between 900,000 and 670,000, which is 230 squared, which gives us something like 52,900 in penalty. So it's much more expensive for us if we make a big mistake in our prediction. Okay, so back to the lines and the houses. So we have this historic data. Let's say we have 4 houses that we know the price of and the number of square feet. And we now want to know which line is best. Which of the 2 lines here in the picture is the best line? So what we do is we say, well, the line that is best is the one that would get the smallest penalty, that will pay the smallest fines if we use it on the training data we have available. Like, because for the training data, we know the actual sales price, so we can figure out what would the penalty be. So for the green line here, for instance, this house up here we know it had an actual sales price of 830,000. If we use this line, we go up to the number of square feet in this house, we go out on the y-axis and see, well, if we had used the green line to predict the price of this house, we would have predicted 820,000. So we're going to pay a mistake or pay a penalty of the difference here, which is 10. We're going to pay 10 squared, which is 100. We're going to pay 100 here. But we're going to measure it on all the houses, right? So we're also going to look at this house that had an actual sales price of 740,000. If we use the green line, we would predict 650,000. So here we're going to pay a penalty of 8,100. And we'll move on like to the last two houses here. The actual price, 380,000. The green line will predict 390,000. That's another 100 in penalty. And also for the last one, we get a penalty. So now we add all these penalties up, and the green line would get a total penalty of 8,700. So that's the green penalty. Now we can look at the blue line here. What would that line's penalty be? So we go over all the houses again, and we can see for each of the houses, we can compute the mistake it's making, we can square it, we can sum up all these numbers, and then we get a total penalty that is much higher, 290,800. In particular, it's making a huge mistake on this last house and on the first house. So the blue penalty is much bigger than the green penalty, which means that we say here that the green line is the best line to make predictions on house prices. Okay. So now we know which line is the best one. Now we need to figure out how can we actually find it? How can the computer find the line with the smallest penalty? Again, the line can be described by this equation, right? Y equals ax plus b, where a is the slope, b is the intersection with the y-axis. So maybe this line is described, the green line is described by y equals 0.8x plus 200 and so on. So let us just maybe to simplify things, start out by saying, okay, let's say I'm only allowed to use lines where the intersection with the y-axis is at 0, just to keep it simple. So I'm only allowed to choose among these lines, and I want to find the best one, meaning the one that gets the lowest penalty. You can write an equation for A. It's not too hard. So you can find a formula. You can just plug in all the house prices in square feet, and you'll get a number out. You get a slope A out. But that's not what we're going to do. We're going to do something different that is closer to what we'll be doing in the more advanced settings later, where we look at neural networks and so on. So let's do a different algorithm, a method for finding the best possible slope of a line to predict house prices when the line has to pass through 0 in the y-axis. Okay, so what we're going to do is we're going to roll our dice and start with a random slope. Let's say this one, 0.2x is our random slope, 0.2. And now what we're going to do is we're going to repeat the following. So we're going to look at the current line, the green line here, and we're going to look at what is its penalty. So this we can compute, right? We just go over all the houses, we check how big a mistake would I make on this house, I square it, sum it all up. In this case, we get a huge penalty, right? 683,100 in penalty if we just look through these four houses. Now, what we're going to do is now we're going to look at another line. We're basically going to take our green line and then we're going to add a little bit to the slope. Like so we're going to increase the slope by 0.01. So maybe it looks like this now. And now we're going to compute the penalty also for this orange line, the one that has a slightly higher slope. You can see, right, it moved actually a little bit closer to all the houses. So all the mistakes are getting smaller in this case, which also means the penalty is getting smaller. So maybe now it's 654,500. So, and then we're going to say, if the new one is cheaper, then we're going to say update our green line by adding this 0.01 to the slope. If it had turned out to be more expensive, we're going to, instead of adding to the slope, we're going to try subtracting from the slope instead and move the other way. So here it's cheaper, so now we go with this green line. And then we're going to repeat this. So we got to, okay, let's try another line that's a little bit steeper in slope. As you can see in this picture, right, it got closer to all the houses, so the mistakes are getting smaller. So this one is going to have a smaller penalty, and we're going to use this one instead. We're going to try a slightly higher slope. It's again going to get cheaper. And we're going to repeat this. The slope gets higher. It still is closer to the houses. We increase the slope again. The mistakes, the penalty is still getting smaller. And maybe at some point when we try, say, this slope, it'll actually start getting more expensive again, right? We're getting too far away from the houses. In this case, right, our algorithm or method tells us to decrease the slope a little bit. So now we're going to go a little bit backwards in slope. And we're going to try again compared to the line with a slightly higher slope. And you can see now we just start going back and forth between two different slopes. And then we're gonna stop when we no longer see improvements in the penalty. Right. So this is one algorithm for finding the best line. Okay. I want to view this algorithm method in a different way, because this is actually the most important algorithm in machine learning and AI. It's called gradient descent. And another way of viewing it is as basically rolling downhill. And I'll try to say this is the exact same method, just viewed in a different way. So the method told us, right, to start with a random slope. So another way of visualizing it is to say, let's have the slope on the x-axis. Like, so as you get further out, you get more and more vertical lines. And we started a random slope, so that corresponds to picking a random starting place in this x-axis. And then let's try on the y-axis to draw what is the penalty on the training data if I use this slope. So basically the algorithm before was let's compute the penalty for the current line. So that means we have a current slope that's indicated by this ball here. And let's compute what the penalty is, like as we started out. It has some penalty on the training data, and we can find it on the y-axis. Now, the algorithm before told us, so let's try to look at a slightly higher slope. So that means move a little bit further out on the x-axis and compute the penalty there. So maybe this is the penalty if we go a little bit further out on the x-axis. And now what we can do is we can see, well, we can try to look at this place and see, well, here it goes downhill, right? So if we go further out on the x-axis, the penalty is gonna decrease. And so the basic idea is to just move downhill, right? We figured out, oh, if I increase my slope a little bit, I'll be going downhill. So I'm going to increase my slope a little bit. And generally, if we had drawn all the penalties for all the different slopes, it might have looked something like this. And what we're trying to do is we're hoping that we will end up by finding a place of the smallest possible penalty, right? We want to end up down here in the valley. And the way we're ending up in the valley is that we're repeatedly looking at where are we now? We're computing the penalty for the current line. We're computing the penalty of a line where we moved a little bit further out on the x-axis. We're going to check, is it going downhill or uphill? And we're going to go in the downhill direction. So we're going to take a step. Here we're going to do it again. And over here, if we compare to a line with a slightly higher slope, we'll see now it's going uphill. So instead of increasing the slope, we're going to decrease the slope. We're going to go backwards. And you can see you're going to end up very close to this bottom of the valley. So this is the basic idea in this gradient descent method for finding the best line, the one with the fewest mistakes on the training data, the least penalty. Now, of course, before we said that our line, it might actually also have an intersection with the y-axis, a b. So we have two parameters, both an a and a b. How does this method change? Well, actually, it's a very simple modification. So gradient descent can also be viewed with when you have multiple of these variables that you're tuning. So now we have both a slope, we have an intersection with the y-axis, we have an a and a b, and we can draw, say, the penalty on the data on the vertical axis. So we're going to start in a random place, and we're going to compute, say, the penalty on the training data at this random place. Now if we for any slope and intersection, there's a penalty, we'll get like a surface of what is the penalty in different locations. So we start in this random place. And now what we're going to do is we're going to repeat the same idea as before. Let's try to change A a little bit and see if the penalty where we are is increasing or decreasing when I change A a little bit. Similarly, we're going to change B a little bit and see whether the penalty increases or decreases. And then we're going to change both of them in the direction where the penalty is going down. Okay, so basically we're going downhill. So this means, and then so we're updating our current A and B a little bit. So we're moving in this direction where the penalty drops. And then we're just going to repeat this. So we're going to look, where are we now? Which direction should I change A and B to make the penalty drop? And I'm going to do that. And then I'm just going to repeat this until I'm satisfied, or I end up at the bottom of a valley here. So now my penalty is as small as I can get it. Right. Maybe one kind of different analogy here is, let's say if you're hiking and you want to find your way down a mountain and you don't have a map or anything, what is it kind of like a reasonable method for finding your way down from a mountain? Well, if you start at a random place, what you could do is you can look down at your feet, and then you see, oh, which direction is downhill here. And then you're going to take a step in the downhill direction. And then you're going to repeat this, right? So that is basically how you can find your way down a mountain, right? Just go downhill with every single step. That's the same idea in this algorithm of gradient descent. Okay. So the idea again was to find the line with the smallest total penalty in the training data and use that one. And then the hope is, and why is this a good idea? Well, the hope is that if the penalty is small on the training data, then because new data, maybe it looks like the training data, then the penalty would also be small on the new data. And a small penalty on new data basically means that we make a good prediction, right? Because if the penalty is small, it's close to the line, and so our prediction is accurate. That's the overall hope. Good. So that was the basic ideas and math behind it. I guess this was like kind of one of the most technical parts. Let's now try to move on to maybe some kind of cooler applications of this machine learning and AI. So the first one we're going to look at are these so-called neural networks and image recognition. I'm going to try and explain how it works. So in image recognition, what is the task? So here in the background, you see a lot of different images. They come from a famous data set called ImageNet, consisting of 1 million images of 1,000 different classes, right? It could be a cat, it could be a horse, it could be a car, and so on. And the general idea or task in this image recognition setup is to have your algorithm or computers tell you what is on this image. And this is like a task that has been studied for a long time. And here in this plot that I'm drawing now, you see historically, going back from around 2010, on the x-axis, you have every year. On the y-axis, you say how many mistakes is your algorithm making when it's trying to predict what is on an image. Humans make about 5% mistakes on this data set, which makes sense. There's 1,000 different classes you have to categorize it into, so it's not a completely trivial task. And if you look here at how well, this is how well algorithms or machine learning has been doing over the years. And maybe one important thing to notice is that in 2012, there was a huge drop in the error rate of these prediction algorithms. And this is the first time you really swapped to using so-called deep learning and neural networks for doing image recognition. Before that, it was closer to, let's say, a hard-coded things that human programmers sat down and wrote code that could handle it. And this is when we changed to like AI and machine learning in 2012 that kind of sparked, I would say, the kind of current hype of AI and machine learning. And already in 2015, computers surpassed humans on this ImageNet task. I say the machine learning or AI algorithms are still not better on, let's say, if you take a picture with your phone in the wild, but at least on this ImageNet data set, it's better than humans. Okay, so so the task is basically something like this. You get in an image like the ones that you see here, and then the AI or the machine learning algorithm has to predict what is on this image, right? And you can see here that it has predicted, for instance, here with a pretty high certainty that it's a leopard. It could also be a jaguar, maybe a cheetah, and so on, right? So it makes some some predictions on what does it think is the most likely thing that's on this image. And here, of course, things get more complicated now because there's not really like before we could draw these straight lines that kind of separated bikes from cars or predicted the price of a house from the number of square meters. But here it doesn't even make sense to talk about a straight line when you have images. Like what does it even mean? Right, so we need something else, some more ideas to make these predictions. Right, we need in particular another machine learning model. So the one that we're going to use is the so-called neural network, which I guess is the foundation of image recognition. It's also the basic underlying idea of large language models, chatbots, and so on. So here we're going to, of course, there are more advanced versions of it than we're going to see in this video, but here we're going to just do the basic ideas of them. So the main intuition is that the human brain is really good at things such as image recognition, text, art, and so on. So the assumption is that if we try to make a machine learning model that is inspired by the human brain, then it will be good at the same things. Right? So the idea here now is to say, so let's just to make it very concrete, let's look at an example where you want to determine the thing that's on this image, is it a cat or a croissant? So we just have two classes and say instead of 1,000 that you have to distinguish. So we have to say, is this, let's say the image is also gray scale, so it's just black and white. And we want to figure out, is this a cat or is it a croissant? So an image, if you don't know, the way that an image is represented is via pixels, right? So an image consists of a whole bunch of pixels, which are single cells that has a color. When it's a grayscale image, it just has a brightness. And this brightness is a number between 0 and 1, where 0 is completely black and 1 is completely white. So this picture of a cat is described by all these pixels that say, what is the brightness in this pixel? The idea now is to come up with a so-called neural network. So we're going to visualize it like this, and I'm going to explain what all these circles and lines are going to mean. But the main idea is that we're going to try to define a mathematical model called a neural network, where this neural network has some inputs on the left side here that we call neurons. All these circles are so-called neurons, and it has one input neuron for every pixel in the image. So the idea is that all these pixels, or these values, the brightness of all the pixels comes into the neural network. It enters it in the left side here, and then somehow it passes through all these layers of the neural network to produce an output. And here in the output layer, there's one neuron for every category. Say there's a neuron for the cat category and there's a neuron for the croissant category. And the idea here is that, as you can see, that we want it to be brighter somehow, and we haven't said what that really means yet, but we want somehow that if we feed in an image of a cat, somehow the neuron corresponding to a cat is going to light up or fire a signal or something like that. Okay, so let's try to make that a little bit more concrete. So we want to try and define a mathematical model of what a neuron is, and this is inspired by the way neurons in the brain work, even though it's not an exact copy. So these neurons are the ones we drew with circles in the previous picture. There's some input coming in from one side, and there's some output going out on the other side along these edges, we call them. These edges should be thought of as connections to other neurons. Now, the inputs, they are basically values that are coming from other neurons in the neural network, except in the input layer that we saw before, the input values are just that's just the brightness of the pixel. Along each of these edges here, each of these connections, there's a so-called weight. So that's just a numeric value that kind of captures how strong is the connection between these two neurons, or the strength of the signal between them. This is kind of meant to reflect how neurons in your brain work. So neurons in your brain are also connected to each other, and they can send signals to each other. And these connections can either grow in strength or they can weaken in strength. And this is really what is happening as you are learning. When humans are learning, the connections between these neurons are either strengthening or weakening. A neuron now, based on all the input and all the weights, is going to compute a signal. So it's going to take each of these input values, say x1, and multiply it with the weight w1. It's going to take the input x2 multiplied with w2, x3 multiplied with w3, and add it all up. So these weights can down or upscale the magnitude of a signal that's coming in. And now it's just going to take its signal and send it to every neuron in the next layer. Here you might in reality do a little bit more, but this is very close to the full thing. So let's say, again, if you go back to this picture, here's our picture of a cat. In the first layer, we just let the neurons take the values that correspond to the brightness of these pixels. And now for the next layer, if we zoom in on one of these neurons, it's connected to all the neurons in the previous layer, and there was a strength or weight on all of these connections. And then we were going to compute the signal, which is going to basically take the weight here of 1.1 and multiply it on to this value 0.6. And we're going to take the weight 0.3, multiply it on to 0.0, and so on, add it all up, and we get a signal of 0.65 in this example. That neuron now is going to have a value of 0.64 that it's going to send now to all its neighbors in the next layer. So basically in comes all the brightnesses of the pixels. The next layer computes its signals and sends them forward. These are different numeric values. Large values are shown with bright light here. And eventually we get to the last layer, and these neurons again have a signal. And then, just as a technicality, at the final layer, you normalize in some clever way all these signals so that the values that you get at the end are non-negative and sum to 1. So it just means that, say, the first one here is 0.7 and the other one is 0.3. They're non-negative numbers summing to 1. The only kind of reason why is maybe you can kind of interpret it as some kind of confidence that the model has that this is a picture of a cat, or this is a picture of a croissant. So let's say it's like 70% sure that this is a picture of a cat and 30% sure it's a croissant. Okay. So then you can ask yourself, how are these weights in the network chosen? Right? That's where all the magic happens. Right? This is what makes it work, is choosing the right weights. And here you again, this is the same underlying idea as we had before in with the house prices and the bikes. We're going to use some gathered training data to do it. And the basic idea is that we have a lot of training data. We know what is on the image. We know this is a picture of a cat. We know this is a picture of a croissant. And then we're going to give a penalty or a fine for if your network with the current weights give wrong predictions. And then the hope is that if we can adjust all the weights so that you have a small penalty on your training data, then the penalty is also going to be small on new data, meaning that you rarely make mistakes. So let's make it concrete. So let's say we have our training data. It's a bunch of pictures of cats and croissants, and we know for every one of these pictures whether it's a cat or a croissant. What we're going to do to train our network, let's say it just starts out with random weights, for instance. Then we're going to take all of our images. We're going to make them grayscale because that's what our network was trained to accept. You could also, of course, make more advanced networks that also includes colors. But for now, let's just say that the grayscale image comes in. We're going to run it through the network to see what it predicts with the current weights that we've chosen. So let's say maybe this is 0.7 for a cat and 0.3 for a croissant. Our idea now is to give the network a penalty based on the predictions that it's making. And we want these penalties to be, well, we want them to give a high penalty if you predict the wrong thing and a small penalty if you predict the right thing. So one way to do it is to say, well, let's look at the correct label. In this case, it is a cat. So then let's look at what did it predict on cat? It predicted 0.7. We're going to take this number and then we want to say, okay, well, if it predicted something close to 0, then we should have a high penalty, right? Because you're wrong. If it predicted something close to 1, we should give a small penalty because it's correct. One such formula is to say, well, if it outputs a value x, so here x is 0.7, what you could do is you could penalize it by 1 divided by x, right? Because, well, if you're close to 0, 1 divided by something close to 0 becomes a really big value. If you're close to 1, 1 divided by 1 is 1. So this is at least some function, some penalty you could give that gives small penalties for correct predictions. Let me just say that in practice, it's a little bit more complicated, but you often penalize by something like the logarithm of 1 over x. So it's not too far from the truth. This is simplified setup with a penalty of 1 over x. Okay. So in this example, right, we predict 0.7. So the penalty we get for this training data point is 1 divided by 0.7. It's about 1.43. And we can look at all of our training data. We also look at the croissant. Let's say it predicts 0.4 and 0.6. So the correct label is croissant, and you predicted 0.6. So the penalty should be 1 divided by 0.6, which is about 1.67. Feed in the next cat, and it's very certain it's a cat, 0.9. So the penalty is only 1 divided by 0.9. Finally, the last croissant, maybe here it's even wrong. Maybe it says it's a cat with 0.8 certainty and a croissant with 0.2 certainty. So here you're going to penalize it by 1 divided by 0.2, which is a penalty of 5. And so now you get a total penalty of 9.21. Okay. Now, how do you choose the weights? And basically, it's the same algorithm as before. We know now if we have already chosen the weights, we can compute what is the penalty that our network gets on our training data. What we'll now do is we're going to try to make tiny changes to all the weights in the network to make the penalty smaller. And then the hope is, again, if the penalty is small on the training data, then the penalty will also be small on new data, meaning it will rarely make a mistake. So what does it look like? So it's basically the same idea, this gradient descent idea that we saw several times already. You just start with random weights in your network. This probably makes terrible predictions. And now we're going to just try to change every single weight just a little bit and see whether the penalty is going to increase or decrease. And then we're going to take all of our weights and change them in the direction where the penalty decreases. And then we're going to repeat. So it basically looks the same way. We're going to start somewhere, and then we're going to change to decrease the penalty. The only thing is that this picture that I drew here is quite misleading because this one has the first weight on one axis, the second weight on the other axis. But this network that we saw before, maybe they have millions or even billions of these weights that you tune all the time. So it's like a billion dimensional picture if you wanted to draw it. But of course, I can't draw this. But that's still the same idea. Just try to change every weight a little bit and see whether the penalty on the train data increases or decreases, and then you move in the direction where it decreases. Again, it's the same as finding your way down a mountain. Look down on your feet and see in which direction is downhill and take a small step in that direction. So we're just using this gradient descent idea to train these networks. Right. So those were neural networks and image recognition. Let's have a look now at these so-called large language models and chatbots like ChatGPT. Right. So I think by now almost everyone knows tools like ChatGPT and chatbots in general, and at least among many other things, they can answer a lot of most exam questions. So here's an example from my course on machine learning, an undergrad course. This is the re-exam, so it's for those that failed the first ordinary exam. And here's one question here. It's not too important what exactly it says. There's some description of a problem, and then you have four choices that you have to answer among. And this exam is 2 hours without any aids, and it's a multiple choice exam with 24 questions. Now, if you look at the distribution on what the students answered in this question here, I can see that most said A and B, some said D, and the fewest said C. Now, it actually turns out that C is the correct answer for this question, right? So they did not perform that well. Of course, I chose one of the questions that they performed the worst on, just to show an example. But let's now try to have a look at what ChatGPT would do with this question. So here I typed in the same question here into ChatGPT with the four answers. So let me write this text and just ask it what is the solution to this. So it's gonna start solving the exercise, and it says the correct answer is C, and it even asks you if I want to see the steps that leads up to it. So it answers it correctly just based on this description of the exercise. Right. So it can answer many of these exam questions correctly, in particular in these types that doesn't require too much thinking and time. Okay. So how did you actually train something like ChatGPT? At its core, the main idea is very similar to neural networks. So it kind of uses a neural network inside with some more tricks on top. But let me try to at least give the main ideas. So the idea is on the left-hand side, input comes in like before. Now it's not an image that comes in, but it's the text or the prompt. So this is this description of the exercise that is somehow being fed into this neural network. Okay, we haven't yet said exactly how, but it is being fed into the network. And on the other hand, on the other side, an answer or response is supposed to come out. Okay, well, let's try to make that a little bit more concrete. Right. So first of all, how do we even represent this input? How is this text represented to the network? And how is the output being generated? So on the left-hand side, the input now is, we're basically going to have one input neuron for every word in the dictionary. And then we're going to have, say, 512 copies of that. So basically, we're going to have 512 chunks of neurons where there's a neuron for every word in the dictionary. And so there's a ton of different inputs here, lots of neurons. And on the right-hand side, we're going to have one neuron for every word in the dictionary, right? So there's one over here for every word in the dictionary. Okay. Just to make the visualization a little simpler, let's just say it's only five. You have 5 copies of neurons for every word in the dictionary. Let's see if we just zoom in a little bit on one of these dictionaries. Basically, what we have a whole bunch of neurons here, one for the word you, one for the word cat, one for the word flower, one for the word house, and so on. So lots of neurons. Now, the basic idea when you want to train something like ChatGPT is that you're going to teach it to predict the next word. Okay, so what do we mean by that? So let's say I give it a sentence. You must buy X flour and then an X, and then we ask it to predict what is X. So what do we mean? We basically mean we're going to feed in, you must buy X flour. On the left-hand side is the input to the neural network. Like before we fed in an image, now we feed in 5 words. And then the network is going to make a prediction, it has a neuron over here on the right for every word in the dictionary again. And what we're going to do is we're going to basically feed it through the network. There's still these neurons that are sending signals to each other like before, exactly like in image recognition. So at the end, all these neurons in the output, they're going to get a value. They're going to be non-negative numbers that sum to one. So we can again think of it as a confidence in each of the words. So in this example here, let's say the neural network somehow says, well, I'm 60% certain that the next word is butter. It says it's pretty certain it's not cat, right? It only puts a 10% chance that it's a cat and 0% chance that it's tennis. That's the next word. Which means basically we can go with the word butter here. So now we say, well, probably the next word that you should say in the sentence is butter. Okay, so now we produced a slightly longer sentence of the first word of the response is butter. Then we just ask it again. We now feed it in everything it said so far. You must buy X flour butter, and then ask it to predict the next word, X. So here the network only, in this case, can only accept 5 words. Before we said maybe 512, so you feed it in kind of like the 512 last words. Here we feed it in the 5 last words. So must buy X flour butter. So in particular, we're going to feed in the word that it just spat out. We're going to feed in butter as well. And then we're just going to pass it through the network again and see what it says. And it says, well, it's pretty certain that the next word is and. Then we can continue, and then we can put an and in our text. We can ask it again, what is the next word that you want to say? And then keep going like that. Right? So it kind of just iteratively produces one word at a time. And if you notice, when we tried ChatGPT just before, we also saw that it's writing its response word by word. It's just kind of all the time predicting what is the next word in the response. Good. So just if we want to zoom in on how do we actually represent the word flower here with these neurons, it's very simple. Basically, we as you remember, right, we had a neuron for every word in the dictionary. And if we want to feed in the word flower into the network, all we're going to do is we're just going to say, well, the input value for the neuron flower is 1, and all the other neurons in this chunk are 0. So it's a very simple and naive way of representing it. Okay. How do we choose the weights? Like, how can we actually make ChatGPT do something useful? It's because, of course, because the weights are chosen in a good way. They're chosen so that it's good at predicting the next words. But how do we make it good at predicting the next word? And basically here it's the same underlying idea. We're going to gather training data, and we're going to give a penalty for wrong answers. Exactly the same ideas as before. And then we're going to do this gradient descent again. Same idea. Keep making small changes to all the weights so that the penalty becomes smaller on the training data. Okay. Same framework. And then, of course, we're going to hope again that if the penalty on the training data is small, then the output is going to be meaningful sentences and responses to your questions. So maybe let's just see, how can we train it to predict the next word, and what is the training data? So the training data that we could use is, say, all text on the internet. For instance, I can go to Wikipedia and find the recipe for carbonara. And this is freely available text. So what I do is I can use this text as training data. Particularly, I can, for instance, zoom in on this little piece of the data here, of the text that says a pasta dish made with fatty. So now I'm just going to train my network to predict the next word. I'm going to feed in the first 5 words, a pasta dish made with, and then I'm going to ask it to predict fatty. So that basically means I'm going to feed in all of these words, right? I'm going to see what does it predict, like what are the values it produces for every word in the dictionary. In particular, I'm going to look at fatty, and it's going to output some certainty that the word is fatty. And like before with the images, we're going to give it a penalty that's trying to enforce it to make the right guess. In particular, what we could do is say, well, if it outputs the value X on the correct word, we would like X to be a big number. We want to be certain that this is the right thing, right? So we could penalize it by 1 divided by X, like we did with the images, right? So in this case, we would get a penalty of 1 divided by 0.2, so a penalty of 5, because we had a certainty of 20% that it was fatty. That was the next word. And here the important thing is, again, we have this data available, right? We have all the text on the internet, so we can check what is the penalty that my network gets when I have the current weights, and I run all my data through it. And then, of course, we have all the text. We're also gonna try and move it a little bit, and then we're just gonna try to predict the next word. We're gonna feed in pasta dish made with fatty, and we're gonna ask it to predict curd. So we're just gonna feed it through the network with the current weights, see what it predicts, and maybe it says 0.7 on curd, and so you're gonna add a penalty of 1 over 0.7, and you're gonna do this for all the data on the internet to give you some penalties. In practice, you're going to still use this logarithm of 1 over x instead of 1 over x for various reasons, but it's the same main idea. So the main method or algorithm is still gradient descent, rolling downhill. Start with random weights in your entire network, and then just repeatedly try to change every weight a little bit and see whether your penalty on all your training data, like on all the text on the internet, increases or decreases. And then you're going to change each of these weights in the direction that decreases the penalty. Right. Good. So let's move on to the last example here, generative AI for image generation. So here we're going to look at such an example tool like MidJourney for image generation. So if you haven't seen MidJourney yet, I'm just going to give you an example here. So MidJourney is a tool that can generate images from a text description, right? So here I told it to generate a photorealistic pictures of a cat sitting next to a plate of croissants, right? So related to the topic that we had, and this is probably something you cannot find pictures of on the internet already. And here you see we get four really nice pictures of cats sitting next to croissants. Right, so this is what these image generation tools can do. And here we're going to try to look a little bit in the ideas underlying such image generation tools. So the main idea here is called diffusion models. So let's say we're looking at a slightly simpler task just so I can explain the ideas. Let's say we just want to train a model that can generate images of cats, right? So you cannot even ask it to what you want the image to be. Let's just focus on generating pictures of cats, new pictures of cats that doesn't already exist. Right? So this is, of course, a slightly easier task, but I hope it shows the main ideas. And what we have available for this task is a lot of images of cats already, right? So we have some training data that has tons of pictures of cats. And you could imagine the tool like MidJourney has been trained on tons of images on the internet. So we have a lot of pictures of cats and we want to use them now to somehow generate new images of cats. So how can we generate a new image that's not a copy of any of the images we already have seen? So the first idea or kind of observation is first might be a little hard to see why this idea is useful. So the first observation is that if I have an image of a cat, like the one I have here, let's say it's in my training data, I can easily turn it into an image that just looks like random noise. How could I do it? I could roll my dice and generate some random noise. It looks like this. And then I could kind of combine these two images and say, well, I'm going to use 80% of this image and 20% of this image. And then I'll get this noisy cat over here. Okay. I could repeat this process and then kind of generate more and more noisy versions of my cat. And if I repeat it enough times, then eventually the image just looks like random noise. Right? So we start with the cat, repeatedly add noise, and then we get a picture that's just pure random noise. Now, the crazy idea, if you will, is now, can we train a neural network to go the other way, like start with random noise and then create an image of a cat from it? So how can we do this? So basically, we're gonna train a neural network like before, and we want to train it so that it can go backwards in this chain, so kind of denoising. So we want to train it to take in, say, the red image here. So on the left-hand side, we're going to have an input for every pixel, an input neuron for every pixel in the image. And we're going to feed in the red image here. And then we're going to pass it through the neural network. The neural network has one output neuron for every pixel in the image. So we can think of the output as another picture. And what we wanted to be, to look like the green image, right? So we're training a neural network so that if I feed in the red image, I will get the green image out. The way I'm training it to do it is I'm going to make a penalty based on how wrong it is. So basically, I'm going to subtract off these two images, what it actually produced, and the true green image that I have from my training data, there's going to be some small difference. And then I'm going to make the network pay a penalty that is larger the more different these two are. So I'm basically teaching the network to remove this noise. Now, if I have a lot of training, I have lots of images of cats. I'm going to take all my images of cats and I'm going to just keep noising it and create more and more noisy versions until, again, for all of them, I have completely random noise on the right-hand side. And then I'm going to train my neural network on all of these images, to take one step back in the chain, right? So I'm going to feed in the red image here. I'm going to try to force it to predict the green image by penalizing it for producing something that's far away from the green image. And I'm going to just feed in, I guess, all of these images, asking it to go one step back. And the way I'm going to do it, I'm going to do this neural network has a lot of weights like before, and I'm just going to train them using gradient descent. This basic idea, try to change all the weights a little bit, see how it affects my penalty, and change them all in the direction where the penalty is decreasing. Now, let's say I've now trained my neural network to do this, like to remove noise. How can I generate a new image of a cat that I haven't seen before? Now, to generate new images, basically what we do is we take our dice, we roll our dice, and then we generate an image that is just pure random noise. So no particular, like this is a random image. It's not going to be a copy of any of the random noise images we saw in the train data. It's just going to be a new random noise. And then what we're going to do is we're going to repeatedly feed this image through the network to try and remove the noise and turn it back into an image of a cat. So that's the basically, we pass it through the network, we get an image out that hopefully has a little less noise, and then we're going to take it again, and then we're going to feed this image into the network once again to try and remove a little bit of noise. We're going to feed it back in, and eventually, up here you can see what the training data was. We're just going to feed in this image and feed it through the network. We keep going and going and going, and hopefully the image gets better and better, clearer and clearer, and eventually, as you can see here, the noise goes away, and we're left with a picture of a cat that was not part of the training data because we started from some random noise that was not identical to any of the noise we got from the training data. So that's the main idea that underlie these image generation tools, of course, with extra ideas on top that allows it to take in text descriptions of what you want and generate different images. But this is still the main underlying idea. Okay, so this basically completes all the technical part. Let me just end with mentioning a few technical and ethical challenges that arise from this AI and machine learning. So, at least on the technical side, one thing is that something like ChatGPT and also other of these large language models has, say, over 1 trillion, which is 1,000 billion of these weights that you're changing. And why is that a problem? It's a problem because it requires a lot of expensive computing power to train these weights, to set these weights right. In particular, something like ChatGPT, if you read online, it's estimated that it was trained for around 100 days on 25,000 so-called A100 NVIDIA graphics cards. So if you want to look this up, just the hardware price, if you don't get a discount, is something like 250 million US dollars. And if you wanted to rent this compute power at, say, Amazon or Google without any discount, it would be around $175 million to train it. Right. So this is, of course, insane that it's so expensive. Also, machine learning, like training something like ChatGPT, has a high energy consumption. It has also been estimated, at least if you run these NVIDIA graphics card for 100 days, it would use something like 20 gigawatt hours of electricity, which corresponds to about 11,000 American households for a whole year. Right. So this is, of course, a challenge, and we need better training algorithms, better methods for training them so that it wouldn't be that expensive. Of course, also now that we can generate these images, artificial images and video, and they're getting harder and harder to distinguish from reality, how do we protect ourselves from misinformation and deep fakes? Also, these chatbots can write text that looks like it's a journalist that has written them. How can we protect ourselves? This is something at least to consider for the future. Self-driving cars, maybe you've seen them in particular San Francisco. We have way more driving around. Like who's responsible when a self-driving car is involved in an accident is like a classic ethical question. But it's also, you can also imagine other things as soon as AI is allowed to make decisions that can influence the physical world, these are obvious questions to consider. There's also something like copyright law. It's something that's actively being discussed. Is it copyright infringement when AI is trained on copyrighted text and images that is available online? Uh, some claim it's not because the purpose of AI is not to exactly replicate the data it's training on, it's just learning from it. And so this is an ongoing discussion. Are we allowed to just train on copyrighted data that is available online? What if we allow AI to make decisions again? How can we protect ourselves from AI discriminating against minorities and so on? Will we allow AIs to make decisions that influence our lives, like in court cases? And how do we prevent AI from discriminating? Also, another thing to bear in mind is that if we allow AI to make decisions for us, let's say in critical situations, how can we trust what it's doing if we cannot understand why, for instance, one of these neural networks is producing the output that it does? Like, say, ChatGPT, a billion of these weights, these are just numbers that have been adjusted somehow. And when you feed in a text description, something happens. These neurons send signals to each other, and something comes out. There's no way for us to understand as a human exactly why is this network doing what it's doing, right? It's just been trained on all text on the internet. Why is it behaving the way it is? So how can we trust AI when we cannot really understand what it's doing? My last thing, maybe relating to the costs of this AI, at least the best quality AI currently, it's only the large tech companies that can afford to develop it. Is this something that we can live with? That we really that they can decide the future behind closed doors, the future of AI, uh, where we cannot really do anything. So with all that, I think that's what I wanted to say in this video. I hope you enjoyed it and learned something about machine learning and AI. So thanks a lot for listening in.